Okay. Now I believe last time we did the example with the looking at total energy transfer through the bottom of that copper pot, correct? Okay, good. So from there, we're going to look at the how to modify that slightly to be able to account for multiple layers of different materials, and then we will end on a general sort of calorimetry example because it's a common sort of one that will show up on your homework this weekend, and then that'll be it for chapter 11. As a reminder, there we go. 11 assignments will be due on the 16th at midnight. 12 assignments will be due midnight on the 23rd. The test will open up around this time. I admit I'm not a huge fan of having it do one assignment due on the same day the test opens, but the test will only open that day, so you have to take it that day. It'll be available on WebAssign, and you'll have at least 2 days. I might add another day or 2 onto there that you can take it on your iPod. You can take it when it fits into your schedule, and to make sure that it fits into your schedule, there's no labs that week. So there is lab next week. We're going to do a phase change lab, but this week, no labs. Since we are doing a test out of class, I'm giving you more time out of class. So,
Tuesday, what time are you going to open the test?
I'll probably open it right after the lectures for that day, and I'll leave it open till, originally I would have liked it done by the next class period, but people who have a lab on Thursday then can't take advantage of the fact that their lab time can now be used for their test. So I might leave it open another day or 2 so that everyone can take advantage of that, even if that means I don't see the other lecture the rest of the week. I'm still working on it, but I'm favoring leaving it open through Thursday for that reason.
And like for that one, once you start it, you finish it. Like it's like,
right.
Yeah.
Once you begin, you have a countdown of 5 hours going.
And it's just chapters 10 and 11.
And 12. Yes, those are all the heat and thermo chapters.
like 10, 11, 12, yeah.
Yes. So we'll wrap up 12 here. Have the weekend to work on the homework. We'll address homework questions and test questions overall on this day. And so the test will be open through the rest of the week. So we can continue reviewing on Thursday if needed.
How many questions would you?
Probably about 10 for a test, because I mean the goal of a homework assignment is to take it over a period of time, and it takes you roughly the same amount of effort. It's just you have all week to do it. So about 10 questions. Each
And
one
then-
going to take about 5 to 6 minutes each.
We submit, so like we take it and then we take pictures of our work and we email. You said email.
Yes.
Yes.
It's in my inbox, and I have the notification reminding me to do something.
Oh my God, we don't do that for homework or quizzes, right?
You can send in work for those. If you got something wrong, I can look at it and give you
Okay.
points through the other, through my side of the tool.
Yeah. Okay.
So, some people have already been submitting that, and they've already got some points back, so. Any work you can show me at any point in time can only help you and will never hurt you, even with homework and quiz. Especially if the machine robbed you of points, I definitely want to see what you did, make sure that you get the points you deserve. Sure. There it is. yesterday we were utilizing this formula for thermal power, for thermal conductivity. And this formula is very nice and convenient, but it only works for single materials. You would need the way that this formula is set up, as it currently is, it only accounts for a certain volume of whatever material this is made of. It doesn't account for, say, multiple layers of different materials. For example, most of your beverage receptacles that are designed to be insulating, if not, excuse me, most of the cups I've used are thankfully pretty good at keeping my cold water cold. This is definitely not solid metal. You can, and similar ones you can tell just by picking them up, just by the sound that they make. Odds are what this is a layer of probably aluminum on the inside, and then a layer of either air or styrofoam, and then a second layer of metal for the exterior casing. So the insulative material is probably air or foam. And that means that this formula doesn't work if we're looking at this object as a whole, because it's metal followed by air followed by metal. You could look at each individual layer separately, but that takes time and each one would have its own power. So there's a different formula that is used to look at things overall composites.
If you did do that, would you add them?
Well, that power would be the power through each successive layer. So if you did one layer at a time, it would be, say, 10 joules through the first piece of metal, 10 joules per second through the first piece of metal, 1 joule per second through the second piece of metal, and then maybe 10 joules per second through the third piece again. The air layer kind of slows the whole thing down exponentially. So it would ultimately be even slower than the air by itself, because you also have metal layers. And I don't know off the top of my head the math to combine those three numbers correctly. Now, at the very least, you can know the slowest it would be if it's multiple layers. So, to combine it all together into one formula, scientists developed these two different methods. This is the more metric physics-y version. This is the American Construction Company version. So let's briefly talk about this one, since it has the more familiar terms in it. Telephone, please. Don't want to vibrate. Sorry. Okay, so this top version of the formula should look pretty familiar because it has all the same variables as the previous one in it. The difference is K is normally here, and now it's on the bottom of the denominator, and there's that sigma term there. Refresher, what does sigma mean in the formula? Very good, SUM of. So, if you have, well, let's look at my thermos for example, layer 1, is going to have its own length over K. So it's got its length over the K for whatever type of metal it is. And that constant, whatever we find here, the specific thickness of that layer divided by the K of aluminum, if it's an aluminum layer, will tell us a specific constant for that specific thickness of that material. Then we look at the second layer, and if that's air, it has a certain thickness, and we would use the K for air. And then the third layer would have its length and its material. So to combine these all into one formula, we're literally just going to add all of these ratios together. So the sigma L over K term simply means you add all of the L over K's together. Ad infinitum, and whatever their sum is what goes in the denominator of the fraction. And that is how you can account for multiple layers with the same formula. And since this is still K, the same K as before, we could still tap back and use these constants, the ones we've been using.
So like, you know, A area, won't each layer have a slightly different area? Or are you like, oh, area as a whole?
You raise a good point, because especially with this
Yeah,
shape,
you were talking about like, you had like that layer of air, so like, doesn't that mean the first metal was smaller than the second?
you are not incorrect. So this math might be a little bit flawed for a cylinder. You are correct. This would be the formula as presented here. Would be most accurate for flat rectangular surfaces, like the wall of a building where it's a rectangle of thickness and then another rectangle of the same area, so on and so forth. You are right in that it would be flawed for this shape specifically. There's probably some other variation that we can occur, which is why for our practice questions in the homeworks, we're going to be looking at square things. It would, I mean, we could still do something here, but you are right in that that would need to be taken into account. Now, this is sort of the more metric-y version because we can use our metric thermal constants here. This version is what is commonly seen in American construction companies because, of course, we use the imperial system and we had to figure out the hard way to do it. So, because in construction, you tend to use the same materials over and over and over again. And there's usually a standardized thickness for those materials. You've got bricks that are a specific inch, drywall is usually a specific thickness, etc. So what they came up with is this R constant. R, based on the positioning in the formula, is itself just L divided by K. But rather than have a table of Ks and then do the length of the material over K, since they were dealing with the same lengths over and over again, they just made a standardized table that combined the L and the Ks together. So this chart of R constants, this number represents the L over K for that material and that thickness. So again, like if you're building your wall out of this much fiberglass, you use this much fiberglass, you use this. And thankfully, if say you have one R for 4 inches and you have 8 inches of something instead, you can just double it. So these numbers, if for some reason a homework question doesn't match the numbers presented here exactly, you can multiply, divide accordingly to get to the unit you want. And again, because America, these units are feet squared times Fahrenheit times hours divided by British thermal units. So when you work this formula to find power, you don't get watts as joules per second, you get British thermal units per hour.
What is that? British thermal units?
It is a different unit for thermal energy. I assume invented in Britain. I don't mean that to be snarky. I don't know much about it because it's never really used, at least not in metric physics. So I don't know why exactly it's used as a constant in the American construction industry, but there it is. And just for your records, 1 BTU is 1,055.6 joules.
And your area has to be in feet.
Yes, it does. This is why I'm presenting the two formulas. You can use metric units and the Ks using this method. You can also use imperial units, and these are constants with this version. I'm just making sure to show you both because some of my questions use one, some use the other.
So your temperature is in Fahrenheit.
Yes. This is about the one time, as long as you were using this table, this is the one time that the formula will require Fahrenheit in feet. So, just going to rewrite the new version over here. We'll take a look at a brief sample of that. So, since this is used exclusively for construction, let's look at a wall. It's a very hot day of summer, and outside of your domicile, the hot temperature is going to be 110 Fahrenheit. That's T hot 10. The walls of your house are made up of 4 inches of brick. So we're going to need the R value for 4 inches brick. Then R for 1 inch of fiberglass. And then drywall. We are then told that the walls of this building are 10 feet tall by 20 feet wide.
Wait, why don't we know the thickness of drywall? Or is that never?
Apparently that's just a standard, because if you look at the table, because I wrote it based on this, because we got sorry, no, it does say thickness. We're going to assume half an inch of drywall.
So like they don't tell you, just like assume the R value that it has? Thickness?
Yes, the issue with this question is I wrote it and I forgot to say. The assignments should be more thorough. If they are not, please let me know. So I will retroactively say ½ inch of drywall, which I think is just the industry standard. What would the area of this wall be? Very good. And that would be in units of feet squared. And lastly, the inside cold temperature of the house is 70 Celsius. So, looking at our formula, we were told the information, find the area, we know the change in temperature. We need to figure out, find R for this entire wall assembly. So let's back up just a second and check our table. Brick is 4 inches of brick is listed as 4. 1 inch of fiberglass is listed as 4.35. And then drywall contributes the least, 0.45.
What is, R refers to what? The R of each material is the what?
It is a thermal conductivity constant. It tells you for that thickness of material how much thermal energy is going to transfer through it every second. So the bigger this number, the faster the thermal energy.
Passes through, or
Wait, reverse that actually. It gets a little tricky because of where the K is now. In the original version, since K is in the numerator, bigger K means bigger thermal power, which means that a bigger K in the original version means faster heat transfer. Look here, the metals have very big numbers, thermal energy transfers very quickly through metal. Gases and nonmetals are very slow. The same types of materials in the other version of the formula will still behave the same way. Metals still send thermal energy through themselves very quickly, carbon still very slowly, but the K, if we look at R as a function of L over K, it's now in the bottom of the denominator. So in this version of the formula, K will still have the same effect, but if we're looking at R values, if we're just looking at R as a function of L over K, if K is bigger, that makes R smaller. Which means that it's reversed if you're just looking at the R for a material. For R's, a small R makes it faster transfer.
which, I mean, in this case makes sense because the drywall is 0.5 of an inch versus like the brick.
Right.
So that does, yeah.
Yes. So it's still the same logic for what material does what is still the same. The only difference is where the K went and how it affects R. So, yes, and the best material up here for insulating would be the 6 inches of fiberglass. That's at the highest R up here, which means it would have the slowest thermal power rating.
Wait, no, I thought slowest.
K,
Oh, yes,
big
yes,
means fast.
yes, yes.
R, big means slow.
Yeah, heat transfer.
Yes,
Yeah, okay.
purely a heat transfer.
Okay, sorry.
Big K is fast number, big R is slow number. Pardon me. Okay, so we've listed the R's for all of our things. So the formula asks for sigma R, we just add them all together. So as we start plugging in numbers, thermal power equals our area, 200 feet squared, times our temperature difference. Because our R is in terms of Fahrenheit, this is the one time we can use Fahrenheit. And for R, we've got 4 plus 4 plus 4.35 plus 0.45. However many material layers there are, you just add them all together.
British thermal units per hour.
Correct. The final answer will be in BTUs per hour.
I'm at 909.1.
Very good. That's what I have too. And just looking at the conversion for a second, that would relate to 900, nearly a million probably, joules per hour, which is a lot. But, no wait, it's an hour, so divide by. That would be about 266 watts, joules per second.
I have a question.
Yes.
So, okay, house has the layers, and okay, and then you have a thermostat, and does the thermostat have to work harder in the winter or in the summer to keep a temperature? Because I know we're talking about like transfer and that kind of thing, but does that depend, and I know you talked about the greater the difference of temperature, the faster the heat transfer,
Correct.
yeah. But does that mean that it should be equivalent because there's a heat difference from like cold to 70 and hot to 70? So it should be the same or it's not the same?
So, this is the hottest day of summer, for the sake of this question. Which means that every single second, thermal energy is leaking into your house. And your air conditioner, if you want to maintain 70 degrees all day inside, the air conditioner would need to remove energy at the same rate it's leaking in. And so the bigger the difference, the more and harder the machine has to work to do that.
So it doesn't matter if it's cold or hot, but the difference has to be the same for the thermostat to work equally hard. Doesn't that make sense? Or no? I feel like it's a weird question, but I don't know.
To maintain the desired indoor temperature, here's your general rule, hot or cold outside. To maintain whatever temperature you set inside, the building has to, on average, over the period of the day, remove as much thermal energy as leaks in, or create as much thermal energy as leaks out. Either way, the total in and out need to be equal for the building to remain in homeostasis. Now, how hard that is depends on the temperature differential, because if the difference is bigger, the rate of energy flow will be more, meaning the machine has to work a lot harder. What also matters occasionally is whether or not it's summer or winter and what type of heating or cooling your home uses, just in terms of like energy cost. Because typically speaking, if you're using an electric air conditioner versus an electric heater, it's easier to use electricity to make thermal energy and warm up than it is to move thermal energy around using electricity. So staying warm in the winter, generally, just with electricity, should be less expensive than staying cold in the winter in the summer,
Okay.
just because it is far easier to intentionally make thermal energy than to move it or remove it. Making thermal energy is easy. Do anything and you make thermal energy. But I think your original question is about, was referring to the difference between the two numbers. The bigger this difference, the harder the machine works and the more expensive things get.
Yeah.
So, in my older, cruddier apartment, I would have to keep the thermostat at like 78 to 80 in the summer to keep from, that was low enough to keep me from boiling, but high enough that it didn't break my bank completely.
80 is really high.
I know, it was in Augusta, and it was a poorly insulated, single-story building. The sun was beating down directly on me. But you get used to it, I guess. My current apartment, I'm on the ground floor too, and I have much better insulation from the sun. Okay. With that, we've now seen and used every individual formula that will be on the homework. I do want to work a different, slightly older, a different practice question with, because we did some similar things, but not one exactly like this, and I want to review before setting this homework. This is another calorimetry question, and it's a good example of how this is used in modern chemistry or metallurgy. Well, or at least, I don't know if a lot of people would use this specific trick these days to identify metal, because we have like spectrometers and stuff and other identification methods these days. But this is historically a thing people did to try to figure out what things were made of. You just work backwards to find its specific heat and compare it to your notes to see what specific heat that matches. So, describing a physical situation, a metal scientist has a sample of metal. They know its mass, they know it is solid and gray, but that's all they know about it. So they heat it up to 800 Kelvin and then they drop it in a bucket. They know the temperature the water was before they dropped it in, and then they measure the temperature that both the water and the metal are at afterwards. So this is the final temperature for both things. They've reached thermal equilibrium. We are asked, what is the gray metal most likely made of? Now, what should we solve for to try to figure that out? Very good.
But, wait, sorry.
Okay.
Specific heat, another one's called heat capacity.
Yes, those are
Unless-
related terms.
Unless you were given, I mean, this is not a chem class, so you wouldn't really have to convert grams to moles, or would you?
No.
Yeah, so,
In this specific class, I've only been using specific heat
okay,
because that is independent of mass. The table of specific heat is just the material, and then you multiply mass by it
mass
to
in
determine
grams.
mass in kilograms.
Okay, oh,
Sorry. Physics likes kilograms.
Yeah,
because
okay.
we're constantly measuring force in newtons, and if we use grams to determine force, all of our force measurements would be 1,000 times bigger.
okay.
there'll be downsides for that reason. But it makes complete sense to use grams and chems since you're dealing with, small piles of dust. So let's list what we know. Mass metal, we call that MM, is 100 grams. Why did I write it that way? We do like kilograms in physics, so that's going to be 0.1 kilograms. The metal's hot temperature, so temperature, initial metal, or Tim, or Tom, depending on if you like I or O for initial, is going to be equal to 800 Kelvin. We don't know its specific heat, but we will. Dropping it into 1 liter of water, so then what would the mass of that water be? How loud, sorry. Not 1
Okay,
gram.
that's milliliter, so 1,000? No.
1,000 grams.
1 kg.
1
Oh
gram.
my God, okay.
You were correct with 1,000.
Or
Just
just like
units of
grams.
grams. You were allowed to like grams. Here, here's a gram. That was funnier in my head, sorry. You are allowed to like grams. If you're mostly taking chem classes, that makes complete sense. We know temperature, temperature, initial, water, 25 Celsius. And the temperature final for both objects combined is 26.5 Celsius. We're working with water, and water has a known specific heat. So, what formula or formulas should we start from? Very good. So we've got Q equals MC delta T, but this refers to only one of the 2 materials at a time. There's another thing we have to do to set them equal to each other.
You mean the other 1 negative, 1 positive?
Yes.
So like, if you were trying to find the specific heat of whatever, does that mean that my water is the positive one and then the metal is the negative Q?
Correct.
Because the water was heated up and the metal lost heat, like that?
Yes. The object gaining thermal energy here is the water. Losing thermal energy is the metal. So let's combine these principles. The object gaining is the water, so we're going to put the water on the left. We're going to plug MC delta T for all this information for water in for Q gain. So mass, water, times specific heat of water is delta T. And that's the delta T up of the water. It goes up 1.5 Celsius. And on the other side, negative times Q loss, but the metal is what's losing heat, so we plug in the information for the metal. Mass of metal times C of metal times the delta T of metal.
Is that, actually, do you know that?
I don't know.
The delta T?
Well, this was the temperature the metal was at before it
final.
falls in the bucket.
Oh, the final's the same.
After it falls in the bucket, the water and the metal will be at this temperature.
So you need to convert one,
One of them, yes.
so let's just subtract 273.
Yes.
But,
This, sorry.
oh, I'm sorry. And then you could have also added 273 to the 26th one and then subtracted, right?
As long as these two things are the same unit, you're fine.
Because they're, what is it called? Proportional?
Yes.
Yeah,
Kelvin and Celsius units are the same size.
yeah.
So 800 minus 273 is 5. Sorry, one more time.
527.
Thank you. And now we just plug in everything we know. 1 times 4, 186, times this difference. I'll just go ahead and compress that to 1.5 Celsius equals negative times 0.1 times Cm times negative this difference. That would be 500.5. And ultimately, this negative and this negative will cancel. Makes things nice and simple.
They're at 125.
Very good. Now, this number might not match exactly anything on this table, so it's,
Probably lead.
it is probably lead. Why do you think it's probably lead?
It's just the closest.
It is the closest, yes.
And it's gray.
It's the closest and it is gray.
Wait, so if it was like, let's say copper was like super close too, and it was like between the two, you'd be like, oh wait, but copper's not gray. Like that?
Yeah, the three closest values on this table, I consider mercury to be close enough, just for argument's sake. Mercury, lead, and gold. We're told it is a grayish solid. Gold isn't grayish and mercury isn't solid.
What color is mercury?
Usually silvery. It's just silver liquid.
What does it look like solid? Can you do that?
And you can freeze anything at a low enough temperature. I just don't know what solid mercury looks like. My best guess it would probably be something like gallium, since liquid gallium looks like liquid mercury.
Wait, you said it's gray?
Yes.
Then why were old thermometers red? Or they're not, and I'm just being weird.
They might have dyed it to
Oh.
make it look like a different color. Solid mercury. Yeah, it just looks like gallium, just solid silvery, very shiny. And that is all the information you should need to be able to do the Chapter 11 assignments. Do work on those over the weekend. Send me questions as you have them, and we will have sort of a study time for that on Tuesday before we begin Chapter 12. I do want to at least talk about what Chapter 12 will be about, to put it in your heads. These notes will be available for you online soon if you do want to read ahead. So next week, we're going to be discussing the laws of thermodynamics. And you've dealt with all of them before.
Oh my god, there's a 0.
There is a 0. Because we had the 3, we like the 3, but eventually scientists figured that they needed to add this extra preface statement. And rather than suddenly have 4 laws of thermodynamics, we now have the 0th law of thermodynamics. It's like the prologue of the novel.
I do not understand it. If they are in thermal equilibrium with the third object, then A and B are in thermal equilibrium with each other.
Correct. So the 0th law states that if the orange marker is at the same temperature as the pink marker, and the pink marker is at the same temperature as the green marker,
the orange and the green are the same temperature?
Yeah. It's just the communicative property of temperatures.
Okay. Okay. It's just.
It is kind of strange that they felt the need to tack that one on there. It was historically added as a literal prologue law for people to understand that piece of information before the meat and potatoes of the rest of the laws. So, we'll dive into each of these specifically next week. You have dealt with all of them, even zeros. Oh,
I don't even remember the third one. What? Is there like a normal way that they don't say it like that?
like this?
Yeah.
This is the most normal way I've seen it listed.
Really?
I've seen definitions where they specifically tie it into the entropy of crystals. In general, this just means the lower something's temperature, the less entropy it has. Eventually, at absolute zero,
Because
entropy will be
it
zero.
has less energy, so it's not moving as much.
Right.
So
Less
it's less
energy, less
random.
chaotic.
Yeah.
And this law says entropy of the universe is constant, but this law says entropy of one object can be made to be zero. You just have to make everything else around it have more entropy, since that entropy has to go somewhere. You can reduce entropy of single objects, you can't reduce the entropy of the entire universe.
Can you go less than absolute zero?
There's been theories, and no conclusive evidence. When I taught high school, there was a joke between the physics and the chem classes about negative Kelvin, which would probably cause backwards time travel.
We do problems with negative Kelvin, which is, I mean, yeah. I know, like, it wasn't like a real life problem, but like our answer was a negative Kelvin, and I was confused.
That,
But the math was right, I mean.
did this come out of a textbook? Because,
Class,
okay,
notes,
because humans, when they are writing math and science problems, they don't always match the actual reality. I've had some bad textbook problems that you can mathematically solve but make no sense. And I've had problems written by my teachers that you can mathematically solve but they make no sense because the teacher doesn't know the scales off the top of their head. Because I once wrote a problem where a meteor was orbiting Earth, but based on the mass and speed that I randomly picked, it would have to orbit 1 inch above the ground. So, the destruction of the entire planet. There was another problem I encountered where we were trying to calculate the friction on a torpedo as it traveled through the water. But the way the friction worked made it such that the friction was strong enough to stop the torpedo and then send it backwards. So there was a meme for a little while in this department of the anti-backwards torpedo. And then in high school, I did a optics question, tracking the reflection of something into a mirror. And the problem only made sense in the end if there was literally physical space behind the mirror for the light to travel through. Which means I discovered a parallel mirror zone, or a portal to the mirror zone. Welcome to sci-fi. Don't want to keep you. It's Friday. Enjoy your weekends. And send me homework questions if you have, or have a wonderful day.